But today it is Jonathan Eckhardt from Cardiff, and well, current title is Strength Density Program and the Camassa-Holm equation, but you try to change it to Camassa-Holm evolution rather than okay. So about Camassa-Holm equation.
Okay, thank you very much. Thank you very much for coming. So I will talk about something that doesn't seem to be related that much to the current program, but it will turn out to be not too far away at least. And I even managed to, well, mention some periodic problems at one point, but there will be no periodic problems apart from this one. So first let me explain what this Camassa-Holm equation is. So I wrote it down here. So it's a nonlinear PDE in spatial with variable x and a time variable t. It's nonlinear, and it first appeared like 30 years ago, more than 30 years ago, in a paper by Focus and Fuchssteiner within a family of bi-Hamiltonian evolution equations, and it did not get much attention following this article until there was another article by Camassa-Holm who re-derived this equation as a model for shallow water waves. And the main properties of this equation that make it interesting, for example, compared to KdV equation that also models shallow water waves, is first of all that it allows finite time blow-up that resembles wave breaking. And second property is it allows traveling wave and so-called soliton solutions. And this is due to the fact that it's a formally integral equation. So let me explain these properties a little bit more in detail. So first of all, I said it allows finite time blow up, which looks like wave breaking to some extent. So this means that even if you start with smooth initial data, it can lead to blow up in finite time. This blow up, it happens in such a way that the solution stays uniformly bounded in H1 norm, so it stays uniformly bounded in particular. But the slope of the derivative may become vertical in finite time. And hence, this looks like wave breaking. So a typical profile which would develop such a singularity is something like this, where the upper part of the solution would move to the right, and this part of the solution would move to the left, and eventually the slope would become steeper and steeper, and eventually lower. And let me mention that this only happens if this quantity here, which will be important later on, changes sign. So next.
Sorry, is it, I mean, once you have reached this vertical slope, yes, would it make sense to say that we can carry on as a solution, but solution would no longer be a graph of a function? So it would.
No, there's no tipping over. There's no tipping over. No. So it becomes vertical, but in a very mild way. It's not tipping over or anything. And in fact, we will be able later to continue the solutions in a nice way after wave breaking. So then there are these traveling wave solutions, and in fact, you can write them down explicitly in their very simple form, actually. So you just have this profile, which is depicted here, and they just move with constant speed to one direction. And of course, since it's not differentiable anymore, you have to consider this as weak solutions to the Camassa-Holm equation. And I should also mention that there are other traveling wave solutions. For example, you can have periodic traveling wave solutions, or you can have traveling wave solutions that do not decay to zero at infinity, and those will be smooth, for example. So only if you have these traveling wave solutions with vanishing asymptotics, then you will end up with these peak solutions, weak solutions. And I mentioned those solutions, they act like solitons, which means that if you superpose them, they will interact in a non-linear way, but retain their shape. So what you can do is you can form like superpositions of these peak-on solutions, but now the heights and the positions of these single peaks will evolve in a non-linear way. And actually, something like this will be a weak solution of the Camassa-Holm equation if and only if the coefficients satisfy some Hamiltonian system. And the Hamiltonian is given just by the H1 norm of the function u. So you can say that in this case, the Camassa-Holm equation reduces this Hamiltonian system is a finite dimensional reduction of the Camassa-Holm equation. And well, here's an example of such a solution. So you have 3 peaks here, and this one will move to the left, and the positive ones will move to the right, and the higher one is faster and will eventually catch up with the lower one, and actually they will not collide, but the faster one will push the smaller one away and eventually become the smaller one. So there's no collision of peaks here, but for example, in this situation, there will be a collision of peaks. So here, this peak will move to the right, and this peak will move to the left, and eventually will collide, and the slope will become vertical. And this is just like in the smooth case, will end up with blow up. So even in this finite dimensional reduction, blow up happens. So the next property was this formal integrability, which means that you can write this equation as so-called Lex pair. And for us, this means the following. So if you take a solution of the Camassa-Holm equation, then you do something that looks very strange at first. So you form again this quantity we had before, and you plug it into this Sturm-Liouville equation as a weight. So for every time t, you get a spectral problem here. And then what you can do is, well, you can study the spectrum of these spectral problems. So for every time t, you get some spectral data here. And of course, you can ask, why should I do this? And the miracle that happens is that you end up with a linear flow for the spectral data if you have a solution to the Camassa-Holm equation. And in particular, so this linear flow is very simple, and in particular it leaves the spectrum invariant under the Camassa-Holm flow. And this observation, it gives you a way of solving the Camassa-Holm equation. Because if you're given initial data for the Camassa-Holm equation here, then you can compute the spectral data, then you can do this linear time evolution, and then in the end, well, you want to go back here from the spectral data to u, so you want to invert this error here, go down again. But this is the tricky part, because here you have to solve an inverse spectral problem. And this method of solution is not new, so it goes back to this work by Gardner, Green, Kruskal, and Miura from the 60s, who employed the same method or developed the same method for the KdV equation. So the same scheme works for the KdV equation, with the only difference that here the spectral problem is a Schrödinger spectral problem. And for this Schrödinger spectral problem, much more is known about this transformation that takes the potential to the spectral scattering data, and also for this inverse part. So one knows quite a lot for this transformation here, but for the Camassa-Holm equation, for this spectral problem, not much is known about, well, about neither of observations, and in particular not about the inverse transformation here. And well, actually, there is there's quite a lot.
What is psi?
Psi is this transformation that takes u to spectral data, which is not specified yet. And there is something known in the case when this omega is definite. So if it's non-negative or non-positive, then there are some results on spectral theory for going up here, and even for going inverted for the inverse spectral problem. But we want to allow the indefinite case here, because otherwise you won't have any wave breaking or anything. So in the non-negative case, the spectral problem we just had is equivalent to the so-called string problem. So if you consider a string which is fixed at 2 points, 0 and 1, and the mass distribution of the string is given by some function omega, so that if you take some interval, then the corresponding piece of string will have mass given by this integral here. Then the equation of motions for the string are determined by this PDE here, with some boundary conditions at 0 and 1. And if you do some separation of variables, or if you consider this as a Hilbert space valid ODE, then you will end up with this spectral problem up here. Spectral problem for a string, well, with Stirling boundary conditions at 0 and 1 at least. So it looks quite similar, except for this additional potential term we had before. And it's actually very similar to the spectral problem for the Camassa-Holm equation when you have a non-negative weight function here. And, well, what does this spectrum mean for the string? The eigenvalues for the spectral problem with Stirling boundary conditions are exactly, or more or less the frequency for the string. So you can say that the direct spectral problem is determining the sound of the string from the mass density, and the inverse problem is determining a string when you are given some sound. So if you have a particular sound you want to grade, then you can ask whether there's a mass density for a string which exactly produces the sound. So you can pose the inverse problem like this. And well, there are the main two questions for this problem is first of all uniqueness. So can you hear the mass density for a string? So if you hear a string, does it uniquely determine the mass density of the string? And the second question is, what kind of possible sounds can a string have? So if you're given some frequencies, is there a string that has exactly these frequencies? And these two problems were solved by Mark Ryan in the 50s, but unfortunately there's no corresponding result in the indefinite case when the weight W is indefinite. So this is the reason we are interested in this spectral problem with an indefinite W. And first I'm going to show you how the spectrum looked like in the three relevant cases. The first relevant case for applications is when U is periodic. So in this case, you have this usual band gap structure for the spectrum, but it allows much more cases than, for example, for Schrödinger operators. For example, it can be bounded and unbounded from above and from below, and you can have only finitely many bands, and you can end up with an infinite gap in single space. So, for example, the spectrum can be bounded. So it allows much more variety than the Schrödinger problem. And second relevant case is when the function U tends to a finite constant. In this case, you have some kind of a scattering situation where you have absolutely continuous spectrum starting from a constant, and then you've got, well, finitely many positive eigenvalues, and if you're indefinite, you also have infinitely many negative eigenvalues. And then the third case is when U decays at infinity. And in this case, what happens, well, it's more or less like you have a kappa is 0, so your absolutely continuous spectrum will head off to infinity, and what is left is purely discrete spectrum, positive and negative in general. And what I will do is I will only talk about this last case here, and tell you what has been done and what I'm able to do. So if we go back to the scheme here, well, I did not tell you what the sets sigma are, but now since we fixed one of these cases, we can introduce them properly. So we will always assume that U is at least H1, which makes this omega H minus 1, which is not so much of a problem, at least locally, but we will need some additional decay for U. And I will not specify this, but in the following, at all cases I will show you will have enough decay to allow this, what we do next, so to introduce this set sigma. So what is this set sigma? Well, first of all, it contains the spectrum. And the spectrum is simply defined as all the complex numbers for which you have a solution of this equation. That's in H1. And well, as I showed you, this set is discrete, it's real, and it never contains 0. And it will turn out that this spectral data on its own is not enough to uniquely determine U. So we need additional quantities. And I call them logarithmic coupling constants. And it doesn't really matter how they're defined. So they're defined in terms of the eigenfunctions, but this expression will never appear again. So all you should think of this is, for every eigenvalue you introduce an additional quantity, which is defined by this, and which gives you a second sequence of quantities. So for every eigenvalue, you get an additional quantity, and we call them kappa. And they're more or less the same as what people usually call norming constants.
But you can mostly construct the omega, right? I mean, then you have to look at all possible U's which can give you omega, and it's definitely some future normal solutions.
But if omega is h minus 1, I can invert this guy.
Identity minus.
So I can always go back.
As you assume that U decays.
I can always go back and forth between omega and U. Okay, so this is our spectral data. It's the spectrum plus this additional quantities, kappa lambda here. And well, now I can show you what this linear flow is. As I said, the spectrum stays invariant, and this additional quantities, well, they are just linear in time. So it's really a very simple linear flow, and you can write it down explicitly. So next, what is known for indefinite weights? So first of all, since we allow U to be H1, this quantity omega can be a measure. So in particular, it can be a finite sum of Dirac measures. And in this case, this differential equation reduces to a difference equation. And hence, you get finite spectrum. So the spectrum will be a finite set in this case. And this is what I refer to as a finite dimensional case. So when omega is supported on a finite set, and you have a finite spectrum. And in this case, you actually are able to solve the inverse problems, even in the indefinite case, completely. And actually, this has been done by Eckhardt and Migielski. And if you remember those Picon solutions, then this finite dimensional case exactly corresponds to these Picon solutions. So we'll talk a little bit more about this after the next slide. First of all, what's known in the general case, and actually there's only uniqueness results in the general case. So I'm talking about when you have infinitely many eigenvalues. So it started with a paper by Benowitz like 10 years ago, and then some modifications by Brown and Eckhardt, and then some papers by myself. And best known result is contained in that last one, and it tells you that U is uniquely determined by our spectral data if this omega is a real valued measure of total finite total variation. So it doesn't cover the general case when U is only H1. At the moment, no one knows. Well, everyone would expect that it's true, but there's no proof. Yeah, and there are no results for existence. I mean, I'm only talking about the indefinite case. There are results for the definite, for the the semi-definite case. But this is the only results about this inverse spectral theory for this problem in the indefinite case. There are results for the definite case, but I won't mention it here. So, well, except for the ones I will show you later on. So now I want to show you what happens in the finite dimensional case first. So we consider this set of functions U, for which this omega is exactly supported on finitely many points. And as I told you before, this corresponds exactly to this multi-Picon solution, because when omega is supported on finitely many points, then U will look like this, and this is exactly the profile of your multi-Picon solutions. So Your multi-Picon solution, the phase space for the multi-Picon solution is exactly this set U and P here. And as I said, in this case, the spectrum is a finite set. And you can completely solve the inverse spectral problem for this set here. And the solution of the problem actually goes back to work of Stieltjes on continued fractions. And then later, Mark Rainer realized that it can be used to solve the inverse problem for the string equation. And finally, it was applied by Bilsat against Migielski to study the multi-Picon solution for the Camassa-Holm equation. So what is the key observation of Mark Rainer? So if you start with a weight like this, and you consider the corresponding spectral data up here, then you consider this, well, strange-looking function. It's the so-called Weyl-Titchmarsh function, in maybe a little bit of a strange form. But it is the Weyl-Titchmarsh function. It's completely determined by spectral data, where W sigma is just this entire function, the characteristic function for the spectrum. So it's completely determined by your spectral data. And then it was Mark Rainer who realized that you actually are able to expand this function into a continued fraction, where the coefficients of this continued fraction are very simply related to your weight up here. So what you get is, well, 2 times the same functions, and one you have a representation in terms of the spectral data, and once you have a representation in terms of your weight omega. And this allows you to solve the spectral problem in the finite dimensional case. So first of all, you get uniqueness, because you can read off all these coefficients from the large set asymptotics of this function. So if you know your spectral data, then you know the large set asymptotics for this fraction here. And by this, you know all the coefficients in this expansion here. And it also allows you to solve the existence part for the inverse problem. And this is where work by Stieltjes comes in. So you give yourself Stieltjes. So you give yourself like possible spectral data here, and consider this function. And now what you would like to do is expand it into a continued fraction, as we saw it before. And this is exactly what Stieltjes studied, so whether this is possible or not. And actually there is if and only if conditions when this is possible. And it's possible if and only if some determinants are non-zero. And these determinants are just given by these expressions here, where you have moments up here, so it's not really important what they are now. But you have an if and only if condition for being able to expand this function into this rational function into a continued fraction. So if you have spectral data which satisfies this, then by this result of Stieltjes, you know you can expand it. And even from Stieltjes, you even get explicit formula for the coefficients. Now, what you're left to do is you just need to write down your measure omega from these quantities, and it turns out that this omega, if you define it appropriately via these quantities, it will have exactly this as well Titchmarsh function. You have this spectral data here. So if you summarize it, for any given finite set of non-zero reals and constants kappa lambda, given such that you have this constant, all these determinants are non-zero, then you can find a profile U, multi-Picon profile U, such that it has exactly sigma as the spectrum, and this kappa lambda is this coupling constant. So you get a transformation that maps U onto the spectral data, which is now a projection, and it exactly maps the multi-beacon solutions to this simple linear flow, where the spectrum is constant and the coupling constants, well, are linear. And in fact, you not only get existence, but you get explicit formula for the solution for the inverse problem. So you can write down explicit formulas for the multi-beacon solutions as well. And this allowed Biel-Sutting and Zbygielski to get a lot of properties about multi-beacon solutions from the solution of the inverse problem. And another remark is that these conditions on the determinants is actually void in the case when you have only positive or only negative spectrum. So this corresponds to the fact that I told you that you will have no wave breaking in the definite case.
So when you say void, you mean it's always satisfied?
If you have the spectrum here, if it's either non-negative or non-positive, then it will always be satisfied. And this corresponds to the fact that I told you that omega, if your omega function is non-negative or non-positive in the Camassa-Holm equation, then you don't have wave breaking. This corresponds exactly to points where the wave will break. But the disadvantage of this condition is that, well, it seems there is no analog of this in the infinite dimensional case. Okay, so actually I don't think that there is a nice solution for the infinite dimensional case for this problem, and then an analog solution to this problem. But what you can do, okay, so what I want to do is avoid this condition actually, no? So what we first observe is that this linear flow up here does not break at all. So the breaking just happens here, or if you want, so in the inverse transformation here. And actually, it's possible to continue this or to extend, generalize this flow so that it won't break. So you can always continue solutions after blow up.
So, sorry, did you tell us what the linear flow is? I mean, the spectrum remains the same, you said.
Yeah, and this constant here. So, as I told you, you can always continue solutions in a weak sense after blow up, and the best example is probably this multi-beacon solution where you just have a positive and the negative peak here. So we'll consider the symmetric case. And what happens here as well is peaks will approach, and in the limit, the slope will become infinite, and when, well, at the time of blow up, they will just disappear. So one possibility of continuing the solutions after this blow up. So first of all, they have a nice limit as time approaches the blow up time. So one possibility to continue this solution is by just setting it equal to 0 after time of blow up. And this means more or less that those two beacons, they collide and they disappear, and the energy they carry will be lost. And there you call this solution will be called a dissipative multi-beacon solution. But there are also other possibilities to continue the solutions after it's equal to 0. And another possibility is that you just think of these beacons that they just collide and just pass through each other and re-emerge after the collision again. So now they will re-emerge, well, on the other sides. And just now this one will move to the right and this one will continue moving to the left. So they re-emerge after collision and no energy is lost here. And hence this kind of solution is called conservative multi-beacon solutions. But of course the energy is not conserved in this one time when the solution disappears completely. So if you want the proper notion for solutions, for this kind of solutions, then you have to introduce an additional quantity which somehow takes account of this energy that is concentrated in one point. So what one does is one introduces an additional quantity mu that measures this energy. And this collision of two beacons is, in this picture, it corresponds to the fact that mu will have just a single Dirac delta measure at this point of collision. So you end up with the notion of global conservative multi-pecan solutions by adding this second quantity. So now a solution is not just the function u, but also is a pair u, u. And well, this has been done by Eckhardt and Xavier some years ago. And the question is now, can you find an isospectral problem for this global conservative multi-pecan solutions, like you have in the classical case? And of course, if this mu is not present at all, then it should look like the usual spectral problem, but it should be some modification if this mu is present. And in the end, what I came up with was, well, the idea came from a paper of Mark Rain and Heinz Langer from more than 30 years ago, which in the end suggested to look at spectral problems of this kind, where you have a set square parameter here. And this coefficient here is simply the second measure. And in fact, it turns out that this is an appropriate isospectral problem for conservative multi-pecan solutions.
So mu is a positive measure? Or
Mu is a non-negative measure. And for these pecans, it's actually only supported on a finite set. So it's just a finite sum of Dirac measures. So this is now the phase space for the conservative multi-pecan solutions. You now have u and mu, where u has a multi-pecan profile, and this measure mu is just a finite sum of weighted Dirac measures. And more or less, it takes account of all the pecans that may vanish at some point, and which you can't see in the profile u. And for this kind of spectral problems, the spectrum of this, well, it's still real and discrete, and in this case, it's still finite, a finite set again, and you're actually able to solve the inverse problem for this set, and this has been done by Mark Rain and Heinz Langer more than 30 years ago, and only recently realized by Alexei Kostenko and myself that this actually is useful for computing these conservative multi-pecan solutions. And as far as I know, it's very nice, and actually the first application of this abstract method by Mark Rain and Heinz Langer. So let me state the resolution of the inverse problem in this case. So now again you have a finite set and any constants kappa, and you don't have these conditions on the determinants anymore, but you always get a pair u, which has exactly these spectral data. And again, this transformation that takes you mu to your spectral data is a projection and maps conservative multi-pecans to this simple linear flow here. Or if you want to put it in other ways, in other words, you have this phase space here, and it decomposes into isospectral sets, and all these isospectral sets are well, more or less essentially the same as an Rn by means of this transformation here, and the conservative multi-pecan flow is just on these isospectral sets is just mapped onto the linear flow on these Rns here. So you completely linearize this conservative multi-pecan flow. And as I said, there's no condition on the determinants anymore. And this is a good indicator that this may work also in the infinite dimension case. Actually, one can do something in the infinite dimension case as well. But first of all, well, we need the global conservative solution for the Camassa-Holm equation in the general case. So is it possible to, not just for pecans, but also for general solutions, to continue then after wave breaking? And the answer to this question is yes, you can do the same. This has been done by Alberto Bassana and Constantine, and independently by Helge Holtning, Xavier, and it looks more or less the same. You again have, instead of a solution u, you now have a pair, u and mu, where mu now is in general a non-negative finite Borel measure. So it's not discrete anymore, but you can have any Borel measure u. And all this defines now a flow on this space, and this is what I call the conservative Camassa-Holm flow. So in particular, it contains all the usual classical solutions of Camassa-Holm equation, and also this weak solution, of course, and multi-pecan solutions and everything. And question is, well, the isospectral problem, the candidate for the isospectral problem is of course this one here now. And the question is whether this works also in the infinite dimensional case. And the answer is to some extent yes. So what I can do is for not for this whole set H1 cross. So M of R is the set of finite non-negative order measures of R. So I can do it for this subset, which is defined by a decay condition like this. So you have quite fast decay for U and for mu, and for this set you can completely solve the inverse spectral problem. So you get uniqueness, existence, you can reconstruct solutions, and you even get continuity properties between spectral data and your weight. So this is unpublished, but hopefully soon it will be published. So let me state the solution of this inverse spectral problem. So you start off with a set that's supposed to be, or will end up to be a spectrum. It's discrete set, well again non-zero, but now you need some kind of asymptotics for this set. I mean, in the finite dimensional case you did not have this because it's just finite sets, but now you need at least convergence exponent at most 1. And we also want that this sum converges, so that this sum converges conditionally in the sense that these limits exist. And then what about our coupling constants? Well, for these coupling constants, we assume the asymptotics like this. So we want this sum to be finite here. And then with these conditions, we can show that there's a unique pair in our subset D, which has exactly this spectrum and coupling constants. And these conditions are actually necessary as well, so we get a complete characterization of possible spectral data for this set of weights. And again, the transformation, which is again a projection, or if we, well, of course, if we define the arrangement appropriately, it maps the conservative Camassa-Holm flow onto this simple linear flow here, the same one again. Or if you want to put it in other words again, our phase space again decomposes into isospectral sets, which are, well, infinite dimensional now, a bit more complicated. And the conservative Camassa-Holm flow on these isospectral sets is just a simple linear, flow. And maybe I'll end with some results that allow to show me some pictures, and which can't be answered actually by other methods at the moment than these inverse spectral theory methods. And it's the question for what happens to solutions after a long time. So what you expect is usually that the eigenvalues of the underlying spectral problem, they correspond in the long time limit to soliton solutions. So in our case, it will be Picon solutions. So solutions of this form. But here we have infinitely many eigenvalues. And usually in this business you usually have finitely many eigenvalues plus some continuous spectrum, but for in this case of the Camassa-Holm equation, we have infinitely many eigenvalues, so no one knew what to do with this. But everyone expected the behavior to be like this, so that the solution after a long time will look like an infinite sum of single Picon solutions. So all of these sums look like a single Picon, which some phase shift here, and each one of these summands corresponds to an eigenvalue of the spectral problem. And actually behavior like this has already been expected by Camassa and Holm in its first paper they published. And they did some numerical calculations and came up with a picture like this. And then later on it has again, well, McKean gave some evidence that this should be true, but he wasn't able to prove it. So there's a picture now. So how is it supposed to look like? If you start with an initial profile here, then all these lines represent your eigenvalues. So these are the positive eigenvalues here. And well, they accumulate at near the t-axis here. And what you expect is that in the long time picture, you will see this single picons running along these lines here. And the highest ones will be far out, so there's one missing to the far right, and there's one missing to the far left. But they will approximately travel around these lines here, and it should look like this. So this is what this formula down there says. And actually, with these methods I showed you before, in particular with stability properties of the inverse spectral problem, we are able to prove this rigorously. So you can show that your solution actually will be an infinite sum of picons as some error term. And you can give the phase shifts explicitly. And this has been done by Gerhard Teschler and myself for classical solutions. And for this class of solutions I just showed you before, it will be contained in this paper. Yeah. And that's where I want to stop.
Thank you very much. So maybe you could tell us a bit more about periodic case. Are there, I mean, how well the theory has been developed?
Well, it's under development at the moment, and
so nobody knows what to do with it. Is there such thing, for example, as skill discriminant?
The idea is you do the same what you do for this case. You add the second term with the set square parameter, and then everything should work on fine.
But
you need to add the second term, the set square parameter term, and you need to go down with regularity to h minus 1.
But do you do this in the original setup, or you do block decomposition and do it in each sort of fiber space? Or
you mean on finite interval in this case, or on the line?
I mean, do you decompose into problem on finite interval, but with different quasi periodic boundary conditions?
You can
Or do you just
interval.
work with initial periodic problem as it is?
Well, they're connected, right? I mean, so I guess in the end you do both then.
But no, but the second term which we had would be the same in each fiber. I mean, this is what I am asking, I guess.
Yes, it's periodic as well, if you mean that. Yeah.
And is there such thing as a skill discriminant? So some function that, I mean, there is, yeah, implicit.
But as I said, it can happen that, I mean, if you go down to the finite interval, then it can be that your operator is finite dimensional, right? So you can have finite spectrum, you can have only, maybe it can happen that you only have finitely many periodic eigenvalues. So things like this happen, and this would end up in the case when you have only finitely many bands and they're all bounded.
But can you have, well, maybe it's a silly question, but anyway, would you be able to have eigenvalue of infinite multiplicity in periodic case? No. Right. Further questions? Yes.
Yes. So this may be a silly question, but so your spectral problem, I mean, especially with indefinite omega, doesn't really look self-adjoint to me. So how come that the spectrum is always on the real line? I mean, how do you?
I can transform it to something self-adjoint. So you mean with the set square or without the set square?
Actually both.
Oh, in the first case, it's a so-called left-definite problem.
Each one is stable.
So if this omega is a measure, then you get an operator in a grain space self-adjoint, and it's even positive. And since it's positive, it's more or less a self-adjoint operator in Hilbert space.
And with the set square?
With the set squares, it's not an operator anything anymore, but there exists a transformation to a canonical system which gives you something self-adjoint.
Other questions? Okay, let's thank the speaker again.